PAT testing. How hard can it be? It's just plugging things into a box and waiting for a green light, right? Except no, and this is where most people slip up. You do not need to be an electrician to carry out PAT testing, but you do need training, competence, and an understanding of the legislation that sits behind it. You are testing equipment that can shock people, start fires, and take a whole section of a building out if you get it wrong. So in this video, we're stripping it right back and doing the full process properly. User checks, formal visual inspection, and then the combined electrical test using the Megger PAT250. We will walk through continuity limits, insulation resistance, leakage testing, and how those tests change for each equipment class. And we're going to tackle a common question. Does the fuse protect the appliance or the cable? And we'll come back to that later. In the previous video in this PAT series, we covered the legal duties behind inspection and testing, who is competent to carry it out, and the equipment classifications that determine how each appliance must be tested. Now we could put all of that together to follow the procedures which are set out in the Code of Practice for the in-service inspection and testing of electrical equipment. And we're going to start with the first stage of the inspection, the user checks. Most electrical faults are visible long before a tester is plugged in, and the user is often the person most familiar with the equipment. If something is wrong, they'll usually spot it first. First, the user considers whether the equipment has been behaving normally. Any unusual noise, smell, overheating, intermittent operation, that is a warning. If appropriate, the equipment is switched off and unplugged. They check whether the equipment has a legible label if the organisation uses them. Having no label doesn't mean it's unsafe. We covered that earlier in a video, but if the organisation uses labels, then they should be intact. Then comes the visual inspection. The plug, the flex, the casing, the strain relief, the controls, the general condition. Crushed cables, exposed copper, burn marks, loose parts, cracks, missing screws, anything that suggests damage or unsuitability for the environment. If a fault is found, the equipment is switched off, unplugged, labelled so no one uses it by mistake, reported to the responsible person, and removed from service. User checks often stop a lot of equipment reaching formal inspection. They also highlight another point from the code. No amount of testing will compensate for equipment that is simply not suitable for the environment it is being used in. If it keeps getting damaged, the duty holder needs to replace it with something fit for purpose. Next, we move into the formal visual inspection, where competence matters and disassembly may be required. Only trained and competent people should continue after this point. First, check the appliance is being used as it should and in line with the manufacturer's instructions. If a heater is being used as a hammer, this might not be the most suitable use for this piece of equipment. It's very common for electrical appliances to find themselves in locations they shouldn't be, and if you find this, include it in your report. The fuse needs to be checked to ensure it's the correct fuse for the appliance. This will normally be written somewhere, however, if not, we can calculate the current of the appliance to ensure the correct fuse is fitted. Appendix 8 of the Code of Practice outlines the power triangle for calculating current. Let's take this heater. The maximum output is 2000 watts or 2 kilowatts. If we divide 2000 watts by 230 volts, that gives us a current of 8.7 amps. So a 10 or 13 amp fuse is required. This lamp has a fuse of 13 amps. If we took the worst case scenario and managed to fit a 100 watt incandescent lamp, this would only be 0.43 of an amp. This means this lamp could be in fault for a considerable amount of time before the fuse blew, and this is not acceptable. Once the fuse rating has been confirmed, we need to check that the connections are tight, there's no sign of overheating, outer insulation in the cord grip, and confirming that electrical connections are not being relied upon for mechanical strength. Next, we need to confirm that the equipment can be switched off and isolated safely. The inspector must identify how equipment can be switched off for normal operations, for maintenance, and in an emergency. We've done a whole raft of videos on isolation, and I've left links in the description for that. But what is important is that the inspector identifies those points of isolation and they are accessible. This could be as simple as unplugging a device. Emergency stops and brakes need to be tested as well. So back to the fuse. Is it there to protect the appliance? Well, and this may come as a surprise, no. The fuse protects the cable feeding the appliance, not the appliance itself. Think it like this. If you have a cable coiled up behind a desk that you can't see and it begins to deteriorate and potentially catch fire, then we want the protective device to operate in that circumstance. Oh, and don't forget, this video is one in a series of videos I've done on portable appliance testing. And if you really want to test your knowledge, you can head over to Trainer Central. I've left links in the description. And if you've got a question that you want me to answer, then you can send it to willittrip@efix.co.uk. So back to the inspection. The code states that every formal visual inspection needs to be recorded. Those records are what demonstrates to the duty holder that the maintenance regime is active, consistent, and effective. They are the audit trail that shows that equipment is being managed responsibly. Okay, so quick recap. We've done user checks and we've done formal visual inspection, and now it's time for the combined defined inspection and testing. So let's have a look at the piece of kit carrying out the test. A compliant tester must meet the requirements of BS-EN 61010 for safety and BS-EN 61557 for accuracy when testing protective measures. Modern dedicated PAT testers make this straightforward because they bring all the required functions together in one unit. But older or separate equipment can still be acceptable provided they meet the same standards for electrical safety and performance. You must understand how the tester works, what its limitations are, and how to operate without damaging the appliance or yourself. I've been using the Megger PAT250 SRX for the last few weeks on a few PAT jobs alongside the Search Suite app, and having used a lot of PAT testers in my career, I must say I do like this one. Not only is it pretty rugged for site inspections, it's small, easy to carry and easy to use. Even easier through the Search Suite app because it links together via Bluetooth, so all the tests are carried out from the tablet and automatically recorded on the ground. It even connects to this thermal printer so I can do my labels on the go, if the labels are required on the job. It is a dedicated PAT instrument designed to meet the full range of tests required by the code: continuity, insulation, polarity, protective conductor, current, touch current and RCD tests. It also supports reduced voltage installation, testing at 250 volts DC for equipment containing filters or surge protection devices. Okay, let's get into it. We're going to be testing all classifications, including some variations of those classifications: RCD testing, power cord or IEC, and extension leads. This will, when appropriate, include calculations to confirm that our readings are suitable and within defined limits. And we're going to start with class 3. Testing a separate transformer starts with a visual check. If all's good, we need to decide if an insulation resistance test is required. That's because a lot of class 3 equipment are appliances like these chargers and contain electronics, so the risk of whacking 500 volts DC or even 250 volts DC through them is not going to prove much. So a visual check might be okay. But I have an LED driver here that operates at 24 volts and outputs at 24 volts. The only real test I can do here is confirm the voltage, and that's about it. A lot of other transformers don't have an earth connection on the secondary side, so I can't really confirm that the protective conductor is separate. But we log that in the record and make notes as needed. This laptop charger is class 2 FE. The visual check is fine, and I'm going to do an insulation resistance test. But 500 volts DC is not suitable, so we turn it down to 250 volts DC. With a lot of class 2 FE appliances, the leads themselves can be unplugged. This lead is now an IEC lead, but more on that when we get to class 1 testing. I recently visited my local hairdresser and offered to PAT test their appliances for some special hair tonic. And we start with this hairdryer. The symbol is class 2, the fuse is fine, and the casing and lead all look in good condition. This is a handheld appliance, so I do need to give it a good check over to make sure there's no hairline cracks or deterioration in insulation anywhere. So the only test needed for this is an insulation resistance test. As the Megger PAT250 tests between live conductors and earth, then the risk of damaging any components inside is minimal. We also need to make sure that the appliance is switched on, so the test goes to the very end of the appliance. This portable heater is also class 2, so I'm going to test it at 500 volts DC. Again, it's important to make sure that the heater is on. The tester will automatically test between live conductors and earth, and connecting the probe onto the appliance will pick up any breakdown in insulation. I also carry out a leakage test. The PAT250 needs to be plugged in for this because we are putting a voltage on the device to see if it works and if any leakage current appears. This gave a leakage of 0.1 milliamp, which is more than okay, but be aware this device will go live, which is why the tester requires additional prompts to make sure you know it's safe to proceed with the test. Back in the studio, and we're going to test this class 2 drill. This is a good example of how insulation can break down over time, and we need to make an engineering judgment to either remove it from service or return. It passed the insulation resistance test, but it is obvious that heat damage is evident on the casing. But what would you do? Remove from service or remain in service? Let me know in the comments. On to class 1 now, and we're back at the hair salon. And we're going to start with this extension lead. Extension leads are class 1, but the code gives them their own section for a reason. They're one of the most commonly damaged items on site. They get dragged around, crushed under desks, knotted up, and in some cases assembled by anyone who can hold a screwdriver. And when they're left coiled, they can overheat without anyone realizing. The entire length of the flex must be checked, not just the first bit near the plug. Damage turns up where the cable's been pinched, run over, or trapped. If the plug or socket is rewirable, it must be opened so you can verify tight terminations, a working cord grip and functional shutters. If the lead is fused, confirm the cable size and make sure the fuse suits it. A mismatch here is a fire risk. Because this is a class 1, an earth continuity test is required. That confirms the protective conductor runs cleanly from the plug all the way to the socket end. If the extension lead has a metal drum or frame, that metalwork must also be verified as an exposed conductive part. The code also limits the length of 13 amp fused extensions. A 1.25mm squared lead generally shouldn't exceed around 12 meters and a 1.5mm squared lead around 15 meters. Longer cables reduce fault currents and compromise disconnection times. Once a thorough visual inspection has taken place, the testing of an extension lead is simple enough. Plug the lead into the tester and the breakout lead from the tester to the extension socket. This creates a closed loop. We select extension lead and press go. The tester cycles through all the tests to make sure everything is okay. We do need to ensure that the extension lead meets the maximum permitted continuity of the device. But how do we know what this is, and is there a number? Well, yes there is, so let's drop out of this test and calculate our continuity limits. Table 10.1 of the Code of Practice gives us the continuity limits for protective conductors. For our extension lead, this is the top row and has a limit of less than or equal to 0.1 ohms plus R. But what is R? R is the expected calculated resistance of the cable. To work that out, we need to dive to Appendix 5, resistance of flexible cables. We are given a couple of formulas here, but the one we're going to use is the one that gives us resistance. So our extension lead is 15 meters long and has a cross-sectional area of 1.5mm square. That gives us a resistance according to table A5.1 of 13.3 milliohms per meter. So by putting this into our formula, 13.3 milliohms multiplied by 15 meters, then divide by 1000 to standardize the unit, we get a resistance of 0.2 ohms. Adding the 0.1 ohms to that gives us a limit of 0.3 ohms. And we can set these limits in the CertSuite app, so we don't need to calculate them every time we test an appliance. Next up is the insulation resistance test, and I'm happy to smash 500 volts DC through this extension lead. However, if we have a lead with USB connections or surge protection, then we need to be careful. A test at 250 volts DC would be okay, but may interfere with the results as the surge is designed to divert high voltage down the earth. So the extension lead is okay, logged and worthy of a sticker, but not this one. It's a little handmade. Next up is this washing machine. This is a stationary piece of equipment and as it has the presence of water, needs a proper test. This one is also new. We would still be under the manufacturer's warranty, but we will give it a test and add it to the register. Plugging it into the PAT250, we connect the probe onto the metal chassis. The probe is critical as this creates a continuous loop through the exposed conductive parts of the appliance, through the protective conductor, down the flex to the earth pin and back again through the probe. We are looking for nice low readings, anything ideally under 0.1 ohms. An IR test at 500 volts DC and that's that machine done. This kettle is next, and be sure it's not been recently boiled before you stick your hand in. Depending on the kettle, you should be able to access the metal plate or element to get a good earth connection. You need to make sure as well that the kettle is on its base or plugged in with its lead. This kettle though has a problem. Kettle's failed. I'll just fix it then. So that was just a loose connection in the plug which I've repaired, and I've made a note on that for the repairs register, and more on repair registers in the next video. The last appliance to test is this heater, which is fixed to the wall and controlled from a switch fuse spur. This is fixed equipment, and on this job it's not forming part of the fixed wiring maintenance regime, so we need to test it. This is where training and experience matters as safe isolation is needed. Once switched off, we unscrew the front plate and disconnect the CPC of the flex. We can now, using the probes and this breakout lead, test the protective conductor. I now put the probes on the line and neutral and carry out the IR test. Next up, we're going to test this IEC lead. And for this test, the PAT250 does all the work. At the back, you plug in the IEC lead and plug the plug into the tester. To test, we use the extension lead setting. IEC leads are very common in office environments, and sometimes it's easier to just unplug the IEC leads and test them in isolation. This reduces the risk of putting any dangerous voltages through electronic equipment, but confirms that the lead is in good condition and fused correctly. It can mean that you spend time under desks having to get hold of the leads, but it is one of the easiest of appliances that we can test. Next up, we're testing this RCD plug. We need to ensure that the RCD will trip in the event of an earth fault. To do this, we plug it into the PAT250. We then plug the breakout lead into the RCD plug. The PAT250 does need to be plugged into the mains for this, as it is a live test. The tester will automatically cycle between 0 degrees and 180 degrees of the sine wave, and is going to test at times 1, and times 5. So there we have it. We've covered every stage of the inspection and testing process, why each test exists and what the results actually mean. But we're not finished yet. In the next video, we're getting into one of the most misunderstood parts of PAT testing and debunking another myth. Does PAT testing really need to be done every single year? That video is on screen right now.